Hello and welcome to Thermal Lesson 2. Today's lesson is going to be on specific heat capacity, and it's going to be divided into two parts. Part 1, we're going to look at the theory for specific heat capacity, and in Part 2, we'll briefly look at practical methods to determine the specific heat capacity of different materials. This will require an actual practical, which obviously we're not going to do at this time. But when we return to school, we will do this practical. So let's make a start. Firstly, what I'd like you to do is to pause the video and complete these questions as a recap from last lesson. Okay, hopefully you have managed to complete these questions without too much difficulty. I will now provide the answers for you. So please pause the video again and mark your work. So on to today's lesson. What I would like you to do first of all is to pause the video and have a little think through this question. Okay, so hopefully you have remembered some of your GCSE physics, and hopefully you've thought of a couple of things. So when you unwrap your food, you are touching the foil. Now the foil and the food are both at the same temperature because they've both come from the oven, so they'll both be at, I don't know, 150 degrees Celsius. So it's not to do with temperature. However, it is more to do with the amount of energy that they can provide to your skin. So when you touch the foil, it actually doesn't store that much energy. So the heat transfer, and heat is of course the flow of energy, the heat transfer is not that great to your skin because it's extremely thin and its mass is actually quite small. So though it might be at 150 degrees and should burn you, it doesn't transfer enough energy to your skin to actually burn you. If you were to bite into one of the pieces of food, actually they have quite a large mass and they contain a lot of water, particularly, we'll talk about that in a bit, but they have a large mass, and so they can transfer a lot of energy to your skin or to your mouth and will therefore cause a burn. So this leads us nicely into what heat capacity actually is and what it means. So specific heat capacity is the quantity of heat required to raise the temperature of a unit mass through a unit temperature rise. Now, unit temperature or unit mass, of course, just means one, so 1 kilogram, 1 degree. And quantity of heat is otherwise just known as energy. So if we look at a formula, we can see this in formula. So delta Q is the change in heat, either heat supplied to the material or heat given out by the material. M is, of course, the mass in kilograms. C is the specific heat capacity of that material. And delta theta is the temperature change. So this is a very important formula. It might look slightly different to how it looks at GCSE because these are the more accepted symbols that are used. Just for your knowledge, Q sometimes is replaced by E, and theta is sometimes replaced by T. Importantly, it is a change in temperature. So have a little think about what that might mean for the units of temperature. So because it's a change in temperature, it actually doesn't matter what units you use. You could use degrees Celsius, or you could use, as the formula shows here, degrees Kelvin. The change will always be the same because, of course, a change in 1 degree Celsius is a change of 1 degree Kelvin. So water is a very interesting substance because it actually has a very high specific heat capacity. So here it tells you that it takes 4,000 joules of energy to heat up 1 kilogram of water by 1 degree Celsius. This is telling you that the heat capacity of water is 4,200 joules for every kilogram that you want to heat up by 1 degree Celsius. So if you're heating up 2 kilograms by 1 degree Celsius, you would need 8,400 joules. If you wanted to heat 1 kilogram by 2 degrees Celsius, you would need 8,400 joules. If you wanted to heat up 2 kilograms by 2 degrees Celsius, you would need 16,800, and so on. So the heat capacity, it literally just means how much energy does it take to heat up a kilogram by 1 degree Celsius, or equivalently 1 degree Kelvin. And this is actually a very, very high value, which is very interesting because it makes water a very good coolant, and it also means that it has other uses as well, and other kind of interesting properties. Let's compare that to some other values for some common metals. You can see that these are in the hundreds of joules per kilogram per Kelvin, whereas this is in the thousands. So it's, you know, a good 10 times as much as any common metal. So do you need to remember any of these values? Not really. But as with everything, it makes a lot of sense for you to remember that metals are, you know, in the hundreds, whereas water is 4,200. One more thing that's also worth pointing out, if you are looking at small amounts, particularly as you might do in chemistry when you're measuring out small amounts of substance, the heat capacity will often be given in grams per degree Celsius. So you'll probably see this value as 4.2 grams per 4.2 joules per gram per degree Celsius. Nothing particularly wrong with that if you're working with small amounts of substance, but of course in physics we're working with SI base units, which are kilograms degrees Celsius wherever possible. Having said that, you will often see this as 4.2 kilojoules per kilogram per degree Celsius. So here is a fairly standard question for you to try. So please pause the video now and complete this question. Hopefully this did not cause you too much trouble. Let's look at the answers. So part A is a very simple calculation. Energy is mass times specific heat capacity times the change in temperature. So if we plug in the mass, the heat capacity and the change in temperature, and it will give us our answer. You could give this in joules or kilojoules, it really doesn't matter. Part B, in this case, the time taken is irrelevant. Sometimes it's important if power is involved, or it's asking you for, you know, rate of heating, for example, but here it's irrelevant. And then finally, in part C, so that should say part C, we're going to rearrange for heat capacity, so energy divided by mass times by the change in temperature, plug in all the numbers, and you should end up with 272 joules per kilogram per Kelvin. So that was a very simple question. In reality, you may well find yourself having to work with more than one material. An example of this might be, you know, dropping a hot lump of metal into a beaker of water, or taking into account the specific heat of a container as oil is heated. So here is a slightly harder question for you to try, although it's still fairly easy. So pause the video now and complete this question. Okay, let's look at the answer. So here we have two things. We have oil and copper. So you can see that any energy we put in needs to heat the oil and the copper up. They of course have different masses and different heat capacities, so we have to treat them separately. The temperature change is the same in each case, and the energy supplied is the same, obviously, because it goes into both of them. So now we're just trying to solve this for one unknown, which is the heat capacity, and you should get this value down here. Okay, let's now look at a much harder question. A lump of iron of mass 1 kilogram has a temperature of 500 Kelvin. it is dropped into 10 kilograms of water, which has a temperature of 300 Kelvin. If you neglect the heat capacity of the container, and assuming that the mass of the water lost to steam is negligible, what is the final temperature of the iron and water? This is a trickier question, but please do give it a go, as it's really good for you to think through things like this. Pause the video now and try the question. Okay, so this does require a few more steps than the previous question, and it also requires quite a tricky piece of thinking. So you might be tempted to just write down something like this and say energy is mc delta theta plus mc delta theta for both the iron and the water. It's not necessarily that helpful to do this straight away. What we need to realize is that we do have iron and we do have water, and that one is cooling down and one is heating up. So the iron is cooling down because it starts at 500 Kelvin. The water is only 300 Kelvin. So of course they're going to reach a temperature somewhere in between the two. And the iron is cooling down and the water is heating up. So that means iron is going to lose some energy and water is going to gain some energy. Importantly, the energy loss from iron is going to be equal to the energy gained by the water, because all of that heat is going to transfer from the hot iron to the cold water, which means this step allows us to write down an equation in a second, but the other thing we need to realize is that the final temperature must be the same as well as both of them. So now both of these two steps here allow us to write down the equations that we need. So the energy change in the iron is going to be given by mass times heat capacity times the change in temperature, and the energy gained by the water is going to be given by its mass times its heat capacity times by its temperature change. I probably should have put subscripts here, so mass and a little iron and heat capacity of iron, and again MWCW, because that would actually make them working out a lot more clear. However, I've forgotten to do it here. So this is the energy lost, this is the energy gained. Now, importantly, what is the temperature change? Well, the temperature change, or a change in anything, is given by the final temperature minus the initial temperature. So that's really important. So here, for the iron, the change in temperature is the final temperature minus the hot temperature. And for the water, it's going to be the final temperature minus the cold temperature, or 300 Kelvin, and the iron 500 Kelvin. So importantly, because this is cooling down, this value here, the final temperature minus the hot temperature, is going to be negative, whereas for the water, this value is going to be positive. So now we can plug in some numbers. Before we do that, because I've just said that this is going to be negative, we could of course make a slight simplification, because the energy change is of course equal. This is equal to this. Because this is negative, sorry, I may have, I haven't explained it very well. This will be negative, but firstly, because this is equal to this, we're going to set it equal to it, and then we're going to, of course, rearrange. So what I'm really saying is there is zero overall energy change, because this energy loss equals this energy gained. So because this is zero, I can say that the energy lost is the energy gained. Now, temperature final minus temperature hot is negative, so that will eventually make this negative sign go away. So now we have the numbers. So the mass of the iron is 1, the heat capacity of the iron is 438, temperature final is what we're trying to work out, minus the starting temperature, and that's going to equal 10 kilograms of water times by the water's heat capacity, 4,200, times by its temperature change, which again is temperature final minus its starting temperature. So importantly, the final temperature must be the same like I highlighted above, which is why this TF is the same in both cases. So now it's just a case of rearranging and solving. So you should end up with this as an intermediate step, and then this, and then you get your final answer of 350 degrees Kelvin. I would encourage you, if you're not entirely sure of this, to either rewatch the video or to pause it and really think through the steps. I didn't explain it super clear at one point, but hopefully now it makes sense with all of these steps shown. Okay, question 4 is a little bit easier. This is going to show you that often they involve some kind of rate or power to make you determine how long something takes to heat up. So please pause the video now and try this question. Okay, let's go over the answer. So estimate the time taken by the mirror to raise 1 litre of water to 100 degrees Celsius. So we obviously need to work out the amount of energy that's needed. We need to know that what 1 litre is. So 1 litre is 1,000 centimetres cubed, and that's a kilogram. And it would also be sensible to think about what the temperature change is going to be. So you could use a range of values here. I've chosen to use 80. If you use 90, if you use 70, that would probably be okay. Roughly, what is room temperature? Somewhere between 10 and 25 degrees is probably okay. So plug in all the numbers and you get your energy required to heat it up. And then, of course, 1 kilowatt means the 1,000 joules per second. And so this is now really easy to work out that the time is 336 seconds. Often the power might come from an electrical source, so you might need to use electrical energy as current times voltage times time. Sometimes it's a bit simpler than that. They just literally give you the power in kilowatts. And then part B, comment on whether your answer is likely to be an over or an underestimate. It's likely to be an underestimate because of energy loss to the surroundings. And the rate of energy loss is proportional to the temperature difference, which means there is going to be a faster rate of energy loss at higher temperatures. So the hotter it is, the more energy it will lose, and the more energy you're likely going to have to add to this to compensate. So a few questions for you to think about. So pause the video now and have a little think about these questions. Hopefully you should be able to clearly see the link to heat capacity. So water, of course, has a very high heat capacity. So when you put water on a fire, it takes a lot of energy to heat that water up, which means or a lot of the energy from the fire is going into heating the water up and not heating up the surrounding objects that are on fire. So you are removing heat from the fire, which of course is one of the 3 things you need for a fire, and you will put it out. The 3 things you need for fire are, of course, heat, fuel, and oxygen. So if you can use water to reduce the heat, you will put it out. Why is the apple in McDonald's apple pie hotter than the pastry? Well, of course, apple has a very high water content, which means it stores a lot of energy, far more than the pastry, which has a much lower heat capacity. Now, of course, this question isn't that well worded. Hotter is not a very sensible word to put here because they will be at the same temperature. However, it feels that the apple is hotter because it's transferring much more energy to you and is much more likely to burn you than the pastry. So this is quite a good example of how our everyday language isn't quite good enough for explaining physics, and our sensations don't always match up to the physics. So another very similar kind of example is if you find something that is metal nearby you and you find something that is not metal, so for example plastic or wood, so it could be the top of your table and the leg of your table, for example. If you put one hand on each, what do you feel? So most people will say that the metal is colder than the non-metal. Of course, that can't be true in your room because everything will be at the same temperature. However, we know that metal has a much lower heat capacity than things like wood or plastic, as well as being a very good conductor. So it is able to take the energy from your body a lot faster, and therefore you feel it being colder. And then finally, question 3 should be fairly obvious that, of course, water has a high heat capacity, which means that the sea takes up a huge amount of energy to heat up and releases a huge amount of energy when it's cooling down, which means there is a massive kind of delay in heating and cooling near the sea. So I said earlier that the fact that water has a high heat capacity has a number of interesting consequences. Here are a kind of few examples of that. We're now going to move on to part 2. So feel free to pause this video and return to part 2 at a later stage, perhaps in your next lesson, or equally watch it now, because you will need some of the information to answer some of the questions that I'm going to set. You won't need it for the Isaac Physics questions, so it might be a good idea to pause the video now and complete the Isaac Physics work, but you will need it for the Cambridge questions. So you should watch this video before you complete the Cambridge worksheet. So this is something you would have done at GCSE. We are going to do it again at A-level because it's an important practical to do. It comes up all the time, and it's also a good chance to recap what you did at GCSE. Obviously, we will do this when we return to school. So it's quite a simple practical. You have some object, metal, it could equally be water in a container, and you measure its temperature change as you heat it up. So this here is a heater, and it's connected to a circuit with a voltmeter and an ammeter in. Obviously, we can work out the electrical energy by current times voltage times the time it's on. So we can work out the amount of energy that we put in. We can see how much the temperature changes in response to that energy. And of course, we can then work out the heat capacity for this material. So this slide here just goes over everything I've just said. What you will then do is you will plot a graph of energy supplied against temperature change, where energy supplied is given by the equation on this slide, VIT. So the longer you leave the circuit on, the more energy will be supplied, and the temperature will change. So you should pause the video now and consider these following questions. Firstly, how is heat capacity determined from this graph? And secondly, what simplification have we made to this graph? So hopefully you can or have realized that the gradient of the graph in this case gives you the heat capacity. And the simplification that has been made to this graph is that when you initially turn the equipment on, the temperature will not start rising at a constant rate right from the start. There will be a small delay in time while the metal heats up. So if we go back to the practical, the heater is here, the thermometer is further to the left. So it takes a little bit of time for the metal to conduct all the heat to the thermometer. So the graph in reality looks a little bit like the graph on the bottom right hand corner of this slide here. I'll return to this again in a second. So the gradient of the graph can be used to find the heat capacity. Here is the full equation. And here is a full method for determining the heat capacity. I would suggest you pause the video now and read through this in full. And that concludes the very brief theory on the practical. Like I said, this is something we'll do when we return to school. What you should do now is complete the Cambridge questions, and if you haven't already, the Isaac Physics questions as well.